Alright, are we live? Hello, hello, hello. Hopefully we're here. So hello again with another problem. And let's take a look. So this one is guess number higher or lower 2. Let's give it a shot. Let's take a look. I didn't really bother to look at the other question to find the discussion. I kind of didn't really want to know too much. Playing the guessing game. The game will work as follows. Okay, so there's a couple things here. I think I know what this is. Two things. One, this is probably logarithmic time complexity. I think I know what this is. I think I've seen this before. This is actually a question a friend of mine asked me. Excuse me. And this also could be, if this is like a real game, you may be able to apply game theory. But this might be a different kind of a game. So yeah, I think this is might be a question I've probably seen before. Let me check something before we get into it. Just a moment. Yeah, so okay. And let me just make sure I have the chat open. I do. Okay. Alright, so playing the guessing game. The game will work as follows. I pick a number between 1 and n. You guess a number. If you guess the right number, you win the game. I pick a number between 1 and n. You guess a number. If you guess the right number, you win. Guess the wrong number, I'll tell you whether the number I pick is higher or lower, and you'll continue guessing. Every time you guess a wrong number x, you will pay x dollars. If you run out of money, you lose the game. Minimum amount of money you need to guarantee a win regardless of what number I pick. Yeah, so if you guess the wrong number x, oh, this is a very interesting question. Okay, this is a little bit more involved. Yeah, so we gotta think about this one actually. So sort of the optimal strategy basically is to the optimal strategy for the most part would be it's basically a load balancing question. It's not quite. This is very similar to the egg question. It's called, where you have two eggs, and you basically you want to find out how high up. If you have a 100-story floor, 100-story building, you have two eggs. You want to find out how high up you can drop the egg before it cracks. I think that's what the question is. And we just assume that it's sort of random which floor it is that the egg actually cracks on. And you could also assume that, I guess these are very small stories, something like that. And the idea is at each point that you check, if it cracks, then you've got to go through a linear number. You have to do one floor at a time until it cracks, because you only have one other egg. But if it doesn't crack, then you've got to figure out, well, how many floors up should I go? And it's a load balancing question, because you want to sort of figure out a way to pick how many floors you go up in a way that's consistent, such that in the worst case you'll always have you'll optimize for the worst case. That's it's a worst case optimization type of problem. So this question is similar to that, I think, in that you're trying to figure out, you want to both use as few guesses as possible and also pay as little money as possible. And the thing that makes this question interesting is that there's more weight on picking numbers that are higher up. So if you want to just simply minimize the number of guesses, right, just the number of guesses, which is kind of always pretty good, you want to basically guess the midpoint, and then depending if you're higher or lower, you would guess the midpoint of what's left. more or less. That's a binary search. That's pretty simple. However, the problem is if the number that they're asking about is very high, then you could run into some issues. You actually want to kind of weight your guess a little bit higher up, a little bit high, more than just the halfway point. So I think what you would want to do is something like, I don't know, let's do with an example. So if you had like 6, 0, 1 through n. Okay, let's do like 1 through 6. All right, 6 numbers. 1, 2, 3, 4, 5, 6. The problem is it's sort of like an expected value question, I guess, something like that. I don't know. I don't actually know how to describe it, but you kind of want to guess a little bit higher. Like you don't necessarily need to split what you want to do. Basically, what you want to do is that the cost to operate on this array versus the cost to operate on this array, you want it to be equal, right? So the number of guesses that you would be required, so this is maybe we'll call it g of x here, or g of, I don't know, ab here, and then g of cd over here. You want these to be equal to each other. That the expected cost on the left side, and really there's some index x where b equals x and c equals x plus 1. What you're looking for is that g of ax equals g of x plus 1d. And we could just call these a and b. And really it's g of 1x equals g of x plus 1a. So there's really two variables. Now, I guess the question is, which index do you pick at each point? And such that this is true, right? That the expected cost of sort of one section is going to be equal to the expected cost of the other section, even though the cost is kind of skewed towards the larger values, right? There's so naturally, basically we expect x to be greater than sort of 1 plus a over 2, right? Which is sort of what you would normally just pick a midpoint, either one of these for a binary search. And however, this time around, you're going to want to be a little more judicious about what you pick. Now, it's not really obvious what you should pick. I want to say, basically I think the sum of both sides should be equal. I think that's kind of what you want to do. And because the probability is of the element that you're looking for is the same for all the elements. So I think you really just want to optimize almost strictly on like the weight function. And in this case, the weight function is just linear. Like it's just whatever the element value is. So I want to say something like as the sum I equals 1 to x of sort of, call it f of I, or it's just I really, is equal to the sum of I equals x plus 1 to n of I. And naturally this is x times x plus 1 over 2. And this is the sum of I equals 1 to n minus of I minus the sum of I equals 1 to x of I. Is that right? I think so, yeah. Actually, that's exactly correct. So that's kind of interesting. Is that right? Did I do that correctly? Equals 1 to n minus, this should end up being, basically, this is 1 plus 2 plus dot 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 plus n minus 1 plus 2 plus dot 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 plus x. And so yeah, you end up with x plus 1 plus dot dot dot. Yeah, that's correct. That's interesting. And that gives you 2 times the sum I equals 1 to x equals 1 of I to n, which this is a bit simpler, right? X plus 1 over 2 is equal to n plus 1 over 2. So solving for x, we would get 2x. This is x squared plus x equals n squared plus n over 2. X squared plus x minus n squared. We can multiply the whole thing by 2 as well. 2x squared plus 2x minus n squared minus n equals 0, right? Or you just do this way. So x is negative b plus or minus the square root of b squared minus 4ac all over 2a, and negative 2 plus or minus 4 minus 8 n squared minus 8 over 4. You know what? Let's actually factor out that 2. Okay, this is not looking good. This does not look good at all. I'm a little confused. Well, we're actually just trying to minimize this function, really. Hold on, let's do, really it's f of x equals the difference between these two things. And the absolute difference. Right? Okay. I need some calculus here. Because I'm kind of getting a little stuck. Yeah, we're trying to minimize this difference. Excuse me. Um, I don't know, man. I actually don't know. This might be a lot more complicated than I'm thinking. I actually don't know. This might be a lot harder than I realize. I'm thinking about it. I think it's actually kind of an involved question. I think it's going to take me more than a few minutes. It's already been 17 minutes. Yeah, I think basically we want to write an algorithm that optimizes the worst case for the worst case, optimizes the worst case, and then give the output for that. And the deal is, I think you're not just evening out you want to even out the expected cost at each step. So calculating that though is kind of tricky because it's not necessarily even every time. Actually, that's a good question. It's like, what do I even try to do here? I guess find the optimal algorithm first. This is relatively small, right? If n is relatively small, then I think we can kind of somewhat brute force this. It's between 1 and 200, so maybe we just brute force this. I think what you're going to do is we can calculate these things directly. The sum from the left and the sum to the right when they're closest to each other. It's a little weird. I want to use a derivative to do this, but it seems really bad. I mean, yeah. I just think so. Squared plus x. Wait, what? This seems so bad. There's no way this is right. What am I doing? What are we doing here? If we just assume that this is larger, right, and that this is just f of x, we're looking for an f of x is 0. That's a little confusing. Oh. N is kind of a constant. I mean, what we're looking for should depend on n. I'm so confused. I'm really confused. I don't know what I did. I did something funky. So just assume for a moment. I want to say this is something like a Diophantine equation. Now, we could figure out, that's kind of what we were doing before, we could figure out when these are equal. That'll give you some approximate value for x. You could do that. That's actually not too bad. Because then the actual value for x is either just the number above or the number below. Those have to be the points where these are closest to each other. Right, because it's very clear that this function is not parabolic, but has a sort of an inflection point, I guess. This function, the absolute value, has a looks something like this, where if x is really small, the difference is very large, and then as x gets larger, there's a certain point where things shift, where it gets very close to 0, and then after that, things start getting larger again because the other side of the equation gets bigger, if that makes sense. Because basically what you're doing is you're moving more elements to one, taking from one sum and giving to another sum. And so first, if the first sum is small and the other sum is large, as you add more move more elements over, they get closer and closer to each other, and eventually they pass each other, and the difference gets larger again. So you could just do it that way too. I think that's the simplest way to do it. Just set this equal to 0. And then you can say x equals negative b plus or minus the square root of b squared minus 4a, and c is actually a negative. All over 2a. So this is what you want, plus 2n plus 1. There we go. Yeah, that's what we want, over 2. Okay. And then this is, now, this is going to be greater than 0. So we gotta add. Okay. And then so x is it's basically the minimum of floor of x, roof of x. Yeah, that's pretty much what you end up with for the result. That's what you pick for x. Yeah, but basically, yeah, you would have a little bit of logic in there to pick between these x values depending on which one of these is smaller or is closer to 0, the absolute value of that function. And so that's how you would select the next element. The problem that you run into, though, is that's like the optimal selection, to remove the most elements or rather to not remove the most elements, but to make sure the expected amount of money that you have to pay on each side is approximately the same. It's as close to the same as you can get. And so if you do it that way, where you sort of try to make the amount of money that needs to be paid about the same on each side, and so you can actually calculate all these iterations, right? Then what you can do is I guess the algorithm would then pick, or I guess the number. And if you're right, and assume that you're going to be wrong, right? Where this is the worst case, so assume that you're wrong every time. If you're wrong, it's either lower or higher. Since we try to make it as close to equal as possible, we have two different numbers, so I guess we would need to basically, I think this is the algorithm that we would want to run, and we would want to run this algorithm on every possible case as if it failed, or every possible answer. So we probably want to simulate this algorithm, and for every possible guess, or every possible answer. Because only 200 of them, right? 200 of them that they gave us, right? So probably would want to simulate this and then see what the worst outcome is. But this would be the algorithm to use, I think. This sort of load balancing thing where we try to keep it as even as possible. And the reason why you want to keep it as even as possible is that, yeah, if it'll optimize, keeping things as even as possible inherently optimizes the worst case. Yeah, the worst case. So, however, the way this question has been set up, it's not obvious how to calculate the worst case, like what the worst case would be. I guess the worst case is if the number is really high. No, that's not obvious either, because it's not clear. It seems probably kind of random whether or not which of these, the floor or the roof of this function, which one actually gives you the smaller difference. That actually seems kind of like it's probably random. That's probably how I would do this. I think that's what I'm going to do. It's 30 minutes now. We'll give it a shot. Let's give it a shot. Let's try to write this simulation. Hopefully this is correct. Hopefully this is correct. So auto simulate equals subfunction, subroutine. And our simulation is going to have an answer. And what we're going to do is have another subroutine, which is this guy, which is find x, we'll say, or just like get optimal index, we'll call it that. And get optimal index. Ooh, okay. And we'll have n, and we'll have do very much, do we? We just need n. We don't really need anything for that, actually. This is really just like a helper function. So we're going to say so we'll have not int, but a double. Why does this keep happening? You see that? My cursor keeps changing. It's a little weird. But anyway, double x is going to be 1 plus standard square root of, it's going to be 1 plus 2 times n times n plus 1, right? You take the square root of that, add 1 to it, and divide by 2. It's not going to be integer division, right? That's the, yeah, okay. And we'll say A is standard floor of x, and B is the standard ceiling of x. And we'll say if, and we'll say these two values, we'll say int m, or call it alpha and beta. Alpha and beta, there you go. Or we'll do y and z. So y is x times x plus 1 minus n plus 1. Yeah, so it's standard absolute value of a times a plus 1 minus, I will call this int temp, equals n that particular number is used a bunch of times. So temp divided by 2. So a times a plus 1 minus temp over 2. And then z is absolute value of b times b, b plus 1 minus temp over 2. Yeah, and then we'll say return min of y and z. Okay, no, actually, if y is less than z, ret is equal to a. If y is greater than z, or if z is less than y, actually we'll do it the other way around, do b, y is less than z, ret equals a, and return ret. So this is the index that we want. Yeah, this is like kind of a lot of code to do something that's not too complicated, but basically we can use what do they call that? The perfect square formula, I guess, to find the roots, I guess. Yeah, I guess we're finding the roots of the polynomial. And the reason we're doing that is, or yeah, we're using, what is it? No, we're using, it's not finding the roots, it's Well, I guess it is, yeah. I guess we're finding the roots of this polynomial. Finding the roots of this polynomial, and it's not just a polynomial, it's of a quadratic polynomial. Finding the roots of a quadratic polynomial, and then using that to, really it's just one root, the positive root, or not the positive root, but yeah, just one root of the polynomial. And then I think they call it the quadratic equation. So yeah, we're using the quadratic equation. And then from there, we're able to figure out, there's two possibilities, and where we can figure out which possibility is optimal for this particular guess. And we'll return that choice. So B is if, so Y represents A, Z represents B, and we default to B, and if Y is less than Z, so Y is better than Z, then we switch to A, and we return that index. Okay. Hopefully this makes sense. Obviously this Y and Z, we can just place those right in there, but what we want to do is, so we get this optimal index for X. We simulate with a certain answer, and we're going to loop over all those particular answers for the simulation for N. And the way we simulate, we say basically a while loop. This is going to be something of a, this is going to be a lot like a this is going to be a lot like a binary search. And we have a start and end. We're going to say int to mid. It's going to be start plus no. So here's the thing: the midpoint, or the guess, is going to be actually the get optimal index, right? And so what's interesting about this is this optimal index changes. That's actually something that I didn't really consider. If you move to a different portion of the array, so for instance, getting the optimal index here is quite a bit different from the optimal index that we calculated from the bottom. And the reason is that basically both of these sums are now missing. These sums are shoot. All right, I think we need to do this differently. Yeah, this has to be written differently. Yeah, definitely. Okay. Yeah, never mind. This is wrong. That works nicely for the first guess. That doesn't work well after that. This is starting and ending indices. You basically int, so left it's going to be 0, right it's going to be 0, and you're going to say pretty much I think the easiest way to do this is do one pass from start to end to get the sum. Actually, you might want to use an interval tree to do this to optimize, but I don't think you need to because you have only 200. N is pretty small. You can actually kind of be somewhat leisurely with this. I think I need to go to bed though. Maybe I'll come back to this problem. I think I can finish this quickly enough. But basically, what you're going to do is calculate the sum from left to right, I guess. So it would look something like. So we'll do left, right, and indices. Left index, start, and right index. And we'll say the right index is over here, and the left index is all the way at the end, right? And we're going to say that basically our initial state is the left side is going to be the sum of all the values which we can calculate that directly, right? It's going to be this ending index end times end plus 1 over 2 minus start times start plus 1 over 2 plus start. A little confusing. And then we're going to say for we're going to do something like this. Okay. And we're going to say I want to do something like this. I equals left index I is greater than or equal to start minus I, something like this. Alright, once I is at the start point, and left will be 0, this goes off. The right index, yeah. And then we're going to say difference is going to be left minus right. This is like really taking me a lot of time to program, but that's okay. So current best is going to be int max, and we'll say index equals sort of -1. We'll say if difference is less than current best, and we're going to update the current best index to, I want to say the left index is what we want. Yeah. And it doesn't really matter which one you guess. You just need to get that actually, here's the other thing too. You probably want to guess on, I don't know if it matters which one you guess on. The left side or the right side. Or the one, no, it doesn't. That's where the split's going to be, but which element do you guess? Actually, doing it wrong. You're actually going to miss an element at the end, so it's incorrect. Right, n-1, right side 0, left starts off like this. Well, that's okay. It's actually a little different than that. Yeah, this, by the way, you could just subtract 1. Never mind, I'll just leave that where it is. It's a little confusing, but hopefully it makes sense. Just looking at this, I want to say you can rewrite this like this too. Start and start -1. Yeah, you could. If you close these parentheses and this becomes a subtraction, then yeah, this becomes start -1. Yeah, that's interesting. You could do it that way. We're just gonna leave it for now, though. Okay, so what we want to keep going with, keep doing here is int max current best index. Yeah, so what we do is, right, we leave one element open in between. Yeah. And I think this actually is supposed to be +1. Ultimately. Yeah, subtract 1 first and then add it. I mean, you could add it and then subtract 1 too. Doesn't really matter. Sure. Anyway, yeah, so that's the best guess. Excuse me. And I'm kind of disappointed how long it took me to code that up. That took a really long time. And so our simulation would be start and get optimal index, right, of start and end. And then we'd say if guess equals answer, then return ret or total is, say, total plus equals guess, and then we would say if answer is higher, then n, or no, if the answer is higher than the guess, otherwise lower than the guess. So depending on where the guess is, or where the answer is. So also the start should be 1. So if the answer is greater than the guess, then we want to update our start to the guess plus 1, right? And then if the answer is less than the guess, update the ending to the guess minus 1. And I think that's all you really need to do. So we get our total, and what's going to happen is we return this total, we simulate, and now we're going to say int worst case equals 0, I equals 1, I is less than or equal to n, plus I, worst case equals standard max of worst case, and simulate I, turn the worst case. Something like this, I don't know. TLE. Perfect. No kidding, really. Let's do the other way around. If guess is less than the answer, and if the guess is greater than the answer, if your guess is less than the answer, and then start's got to be guess plus 1. If your end is, if your guess is greater than the answer, then you got to update your end to guess minus 1. And why does this not work properly, after all? Really, TLEs, how does that happen? How does that happen? Where's the TLE on? The first one, huh? Okay. Man, it feels like I have a lot of feel like I'm writing a lot of code where I have these errors. Start and end. They don't change, do they? Mm-hmm. What? Ah, okay. Okay. What is going on here? What is going on here? I think this code's just broken. Guess is 0. What do you mean guess is 0? What? 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 What is going on here? Come on, man. This can't be right. This can't be right. What did I do? What did I do? What did I do? I need to go to bed. 45, 36, 28, 21, 15, 10, 6, 3, 1. 9, 8, 7, 6, 5, 4, 3, 2, 0. Excuse me. That's fine. And why, what is the issue? What is the issue? So there's a difference of 6 here. So that's going to be the right one to pick. Oh, that's why. Ah, well, buddy, what are you doing? Okay, that's a lot better. Except this happens. Left and right guess is 0. Okay. So guess is 6. Alright. Start and end. Oh, okay. So this is what's wrong. Yeah, this is not something you typically have to have issues with, right? Because usually it's with binary search, you just pick the midpoint. This is like a modified binary search where it's not really the midpoint. There's an algorithm to figure out which point to pick. And that algorithm is totally custom, I guess. Or at least I've written it in a way it's totally custom, so it's a little awkward, just say. It's a little unfamiliar, a little awkward. Shouldn't be that bad, but writing it the first time, it's like, yeah, it's pretty awkward. There's got to be a better way to write this, I don't really know. Let's see. Start and guess is 6. And then we say, okay, yeah, that makes sense. Excuse me. Oh, this is wrong, by the way. 7, yeah. So the sum from 1 to 6 is 21, and the sum from 8, 9, and 10 is this guy. Yeah. So that was also incorrect. But okay. So 1 to 6, guess 5. So 1, 2, 3, and 4 gives you 10, and then 7. Oh no. Excuse me. 6. Yeah, 10 and 6. And then you have 11 and 6, right? So I guess 5. And then 1 to 4, you guess 3. And then I have 1, 2, and 4. And it says 1. One, 2, guess 1. Oh. Guess -1. Start and end. Interesting. We're just going to say start. This is if they're equal to each other. Right? Oh, there we go. Oh, word 2 was right. No kidding. Okay. Oh, I don't know. Let's do a whole bunch. By the way, I have no idea if this is correct or not. Nice. It's wrong. After all of that, it's just wrong. Perfect. Do I just go to bed after this? Oh, fantastic. Oh, excuse me. Oh, they're just all wrong. Okay. So you can do better than all these things. Okay, yeah, perfect, great. Yeah, I mean, of course. You know? Oh. Okay. So this is not the best algorithm, huh? Is that what's being suggested? I have this feeling that it's actually better to just do a straight binary search. Just a regular binary search is better. It's just as optimal, regardless of the weight. And the reason being that I don't think so. It doesn't seem right to me. I don't know. It seems like this is the right way to do it. Well, I guess the reason is that you have fewer guesses, and that's just always better. I don't know. Let's see. Let's see if we just do start plus n divided by 2. No, the other algorithm is better, I think. This is like, you gotta be kidding me. Excuse me. This is some kind of game theory thing going on. Somehow we both agree that 7 was the right move. And 9 and 3, huh? Excuse me. Where does this start going wrong? 9, 6, 8, what is that? 1, 2, 3, 4, 5, 6. That's 6. That's when we start having problems. So I am falling asleep over here. Really? So 6 is the one answer, the one true. Output 9, expected 8. You gotta be kidding me. Why? Why? Whoa. Oh. Okay. Interesting. I don't know, man. Excuse me. Wait a minute. Maybe I should have read this, because there are 10 different possibilities for the answer. Am I crazy, man? Am I just doing this wrong? Excuse me. I think I'm doing this wrong. I don't think this is supposed to be a binary search simulation thing going on here. I think this is supposed to be kind of like a DFS type of thing. Depth first search. Yeah, because all these possibilities are mutually exclusive. Also, I think this is wrong. This routine. I'm thinking about it. Excuse me. Alright, if we had 6, let's do 6 by hand. I don't think this problem is supposed to be that difficult. I think I just made it way more involved than it needs to be. Excuse me. So the first guess, we have 11 and 10, right? And so we pick either 3 or 4. See, that's a good question. Which one do you pick? Well, no, this is... That's actually not that hard. It's 6 and 11. It's 4, and then this is... Pick 3, it's 3 and a lot more. Pick 5, it's 6 and 7, 9, 10. Actually, 5 is the best to pick. 6 and 10. Right? Start with 5. And you can go higher. 6 gives you $5. Really don't need to write that. And then you have 1, 2, 3, 4, which I think you pick 3. Gives you 3 and 4. If you pick 2, you get 1 and 7. If you pick 4, you get 6 and 0. So 3 gives you 1 and 2 and 4. Which do you pick 1 or 2? Well, if you pick 1 and it's wrong, you don't pay as much as if you pick 2 and it's wrong. So I think you pick 1. I think that's the key optimization that I missed when you're faced with only 2 elements. Which one do you pick? I think you pick the smaller of the 2, right? Yeah, I think that's that's the base case that I'm missing. Still wrong. Gotta be kidding me. No. Alright, so here in this path, we would say it costs us 5. On this path, costs us 8. This path, this actually costs us 9. How did they get 8? I don't believe you. What do you mean? What if it took you 8? That path is clearly 9. These people are liars. These people are liars. don't believe them. Impossible. Absolutely impossible. How is it even possible? There's no way. There's no way. Oh. I think you were supposed to pick 2. Pick 5, 10, and 6. 11 and 6. No. What? What if you pick 4? No, it's still 9 if you pick 4. How did they get 8 for that? That's not. There's no way that's true. There's no way that's correct. I do not believe you. It's got to be 3 the second time. So that gives you 8 to get to 4. But the problem with that is that you have. What if you do 5, 3, 1? What if it's 2, right? And you guess 5, 3, and no, man. There's no way this is right. No, that can't be right. Oh no, so close to. Or it feels so close. There's no way. There is no way. There is no way. There is no way. There's no way the worst case is 8. If it's 1, what do you do? Guess 1. You guess 5. And that leaves you with paying 5, and you have 6 and 1, 2, 3, 4. And you want to split these in half, I guess. It's not right, man. It's not right. No, dude. No. The worst case scenario. All the possible algorithms that you can do. The worst cases for all of them. I think they're wrong on this problem, man. I don't think it's actually true. Or something, I don't know. I don't know what the deal is. I don't know what's up. Something's wrong. If you pick 4, then you have 5 and 6. That gives you 9 immediately, so you can't do 4. What if you do 3? You have 5, 4 and 6. And then you can do, oh, pick 3 first. No kidding. And then you have 2 and 1. Okay. So I'm just wrong, huh? That was a heuristic I was using that I assumed was correct, but it's not. It's just not correct. Great. Oh man, come on. Excuse me. Well, what the heck? This is definitely interesting. What did I do? I just said try different possible root nodes. See if you can beat the best current. Pick 3. Why would you pick 3 though? Why would you even do that? Why would you think to do that? You wouldn't think to do that. No, never. Why would you ever think to do that? It's definitely not. The only reason why that works is because both of these two get cut out. You want the right side of the tree to be as balanced as possible, basically. Something like that. Excuse me. I don't know, man. I think I have to come back to this. But 10 somehow. It's not that you want it to be that balanced. You just want the. You kind of just want this shape as much as possible. We have like the largest nodes you can on one level on the right side. Seven. Yeah, so you get this 18 gets removed here. And this whole tree over here is this 1, this is 6. It's just 20, this sum is 21 on the left side. Doesn't really matter what you do on the left side because this is the most expensive thing you do anyway. But you can do, pick 3, 3, 5, 6, 4, 1, 2, gives you 11, this gives you 15, doesn't really matter. Not that you can do whatever you want on this side, but you kind of, yeah, it doesn't matter that much. It seems like you kind of want to optimize for the root nodes to be as large as possible, or not the root nodes, the leaves to be as large as possible. Excuse me. I don't know. I think I have to go to bed. I don't know, I didn't come up with a good solution here, but I think it's... Yeah, this is kind of a tricky question. I guess I could see why it would only be 200 for n. I think you gotta do some kind of backtracking where basically you generate all the possible trees that you could have, all the possible binary search trees, and then for each binary search tree you find the best possible path, or for each, generate each binary search tree that's possible, and then for each binary search tree, check every path to the leaf node, and take the sum not of that path, not including the leaf node, and then for each binary search tree find the maximum value, and then what you want to do is you want to take over the minimum over all of the possible binary search trees. That's kind of what I think has got to be done to solve this problem, like to be certain that you have the right answer. No, the problem with that is that there are a lot of possible binary search trees. So maybe that's the right algorithm, but then it would be too inefficient to do it for n equals 200. I actually don't know how many binary search trees there would be. Maybe there's not that many, actually. I actually don't know. I think it's a Catalan number. I'm not really sure. Yeah, we'll do this. I don't remember. Oh no. Doxed. Yeah. Yeah, that's what I was gonna say. I think it's the Catalan numbers. The Catalan numbers are... The Catalan numbers are kind of big. I think they're exponential. Also called Segner numbers. Excuse me. Yeah, that's really big. Yeah, it's exponential. Right, we won't be able to generate all the binary search trees. Brute force will not work here. So you could potentially brute force, but you'd also need to prune, I think. Do a lot of pruning. This question maybe is a little bit harder than I thought. Quite possibly a little bit harder than I thought. It's a good heuristic that I have going on here, but it's not optimal. Right, a good example of breaking this is 1, 2, 3, 4, 5, 6, where it's better to pick 3, because then you can, as opposed to what you would otherwise pick, which is 5. Because you can get the 4 underneath the 5 here, and then you get the 3 and the 5. And you kind of get the 4 for free. What's interesting is that these are all leaves, but the internal nodes are basically split. You know what you probably want to do is, I think I would need to think about this problem a little bit more. kind of want to optimize on the internal nodes, it seems. Looks like you want all the odd numbers too on the internal nodes. Well, maybe that's just a coincidence, right? If you had 7. There's got to be a way to do this more efficiently, I guess. Let's see if we only want odd numbers. 3, 5, 6, and 7. So actually, you probably want 6 over here. So we can put 5 and 7. And then you still have 4 though. So probably want this to be a 4 then. And it doesn't really matter what you put on the left side. You get 2, 1, and 3. That gives you 10. This was definitely, I thought this was going to be harder than I thought this was going to be relatively hard. Yeah, 8 and 10. Very close, but not quite right. Actually, you could do both, I think. You could do a balanced tree and a slightly weighted tree and kind of compare the two. I don't know if that's a good idea. But it's interesting because these are basically balanced trees. Yeah. Sometimes it's balanced and sometimes it's not. I couldn't tell you why. So this is a similar kind of deal. We probably want 7, 8, and 6. And then probably a 5. So I guess it's 12, so let's see what we get for 8. Okay. That gives us 8, 9 on the left, 12 on the right. Probably actually do better than 12, probably do 11. Could put the 4 here. No, but then you need to put 5 to the right somewhere. Which I think doesn't really work out too well. Yeah, 12, okay. That's pretty interesting. I don't know if this is always true, but basically it looks like you pretty much always want to I don't really know. I don't really know what the algorithm is for this trees. Not really seeing it. I feel like I'm missing something here. -9. Probably want 8, 9, and 7. Yeah, I think I have to think about this some more. I don't know, I'm not seeing it. Probably want the next largest number you can here, 6. And then here. Now here's the thing, is you could put something else here for 6, so you probably don't want the next largest. You probably want, see, this is actually not true. You could put a 5. No, you could put, no, yeah, you could put a 6. A 5. And actually you would then do 3, I think. 5, 4, 1, 2. Really be 4, 5 probably. This is 14. And then this is 13. And this is 10. Now, what's really weird though is as soon as you get to 10, that's when things get kind of funky. Yeah, I don't know, man. I would have to think about this problem for a while, I think, to come up with a better approach. I'm wondering if actually just a simple, like, pruning type of thing is warranted. Like a brute force with pruning. Maybe that's the way to go. But here you would do 10, 10, 8, 9, and then 7, and then everything to the left of that, which gives you probably just want the middle element, which would be 3 or 4. 3 is fine. Yeah, so 16, and then the other stuff doesn't matter that much. You could do, you just need to put the 4 and the 6 sort of in between on the 5. If you put 4 here, it would work also, I think. You know, what's interesting is actually you would want the optimal. Oh, this is somewhat dynamic, somewhat recursive, right? Because this is the optimal for this guy, right? 1, 2, 5, 4, 6. Oh yeah, look at that. Ah. Oh yeah, we should use dynamic programming to do this. Find the best possible with the elements that are left over to the left. So these 6 are sort of what do they call that, a recursive call. And then you want to put these 3 sort of in one section. And then this becomes a parent, and then this is a recursive call. Well, that's pretty simple. And then here you do similar things. So these 3 get their own section. This becomes a parent, and then you do a recursive call here. Oh yeah, just do this recursively. Same deal, 6, 7, 8 becomes its own piece here, and this is a recursive call. 1, 1, 2, 3, 4. Just exactly what we did here. Alright, 6, 7, 8, 5, yeah. This is 5, 6, 7. Head, recursive call, 1, 2, 3. And then 1, 2, 3, 4, 5, 6. This gets its own section. This is the head. Recursive call. Excuse me. This always has the same, what do they call that? The same form. And then finally, one, two, three, four, five. What does 1, 2, 3, 4, 5 look like? This would get its own section. This would be the head. And this is sort of a base case. Right? So you have 2, 4, 3, 5, 1. So 5 I think is 6. Yeah. And then finally 1, 2, 3, 4. You put those in its own section. 3, 4, 2, and then 1 would be the parent, so 4 seems to be optimal for 1, 2, 3, 4. Yep. And then for 1, 2, 3, this is also kind of a base case, which is just going to be 2, 1, and 3. That's a good question, actually. What does 1, 2, 3 get? I think it should be 2. And then finally, 1, 2 is also kind of a base case, I guess, which is just 1, 2. It should be 1. So there's three more elements. What you're going to do is take through those 3 elements, put them to the right side, and really what you're going to do is make the root node the 4th element. So you take this middle element, make this the root node, and then you recurse on the smaller values. Something like that. I wonder what this would look like. Well, that code, man. Oh boy. Oh boy. Alright, so let's see. Base case n equals 1. So really if it's 1, so base case is n equals 1, turn 1, n equals 2, turn 2, n equals 3, turn 2, n equals 4. Alright, now n is greater than or equal to 4. I'm going to do the following. Actually, yeah, well. So, I guess what we do is we say total is going to be say right is going to be, the right side is going to be n minus 1 plus n minus 1 plus n minus 3, right? And then we're going to say left is going to be get money amount of n minus 4. Alright, so we make this 3 branch on the right, make this new root node, and now we have the left side of the tree. That's the n minus 4 portion. 4 nodes removed. And I think if it's 0, we just return 0, by the way. And we'll say, so we have 4 or more nodes. If there's 4 nodes, I think we could do that one too as a base case. That way we don't need this base case. The reason I want these base cases is that way n over n minus 4 has meaning. N equals 4 is, it's going to be 3, 2, and 4 on the right side, and then 1 on the left. So I think it's 4. It's for 4. And then get money amount n minus 4, and then return standard min of right and left. Oh no, max. Yeah. Well. Yeah. Something like that. 2 is 1. Oh. That's my mistake. Yeah. Does that work? Wrong. I did 0? Really? Oh, that makes sense. The last 2. Also, this should probably be left, right. But anyway. 4 and 5. Wait, why? Oh, where did that come from? Okay, it looks correct so far. Alright, let's see how we do. Wrong. Nice. It's also very wrong. Well, okay. Yeah, I think what starts to happen is the right side is more than just the, the first few elements, I guess. Basically, this is assuming that we don't have a parent for this node, is we would do it this way. It's not correct. Yeah, I think as soon as you get past like 16 nodes, it starts to get interesting. Actually, pretty quickly. Oh man, challenging question. Challenging question. I really do go to sleep. A little too tired. It's the third one, which is 12. You almost immediately. This is not correct. Very quickly. Right, when you look at 12, it starts to get interesting. 1, 2, 3, 4, 5, 6, 7, 8, 12. We would say we want this section here, 10, 12. Probably want this parent to be the largest possible. So we'll say 9. No, it doesn't have to be 9. Could be something else. It seems 9 is better, possibly better. Let's put 9 there, and then we need potentially children for 9. Do 6, 7, and 8. But what parent? Make that 5. So that's 25. That's not what we want. This is 20. If we put, somehow we get 21. Well, okay, hold on. Okay. This isn't good either because this is 16, and if we have anything below here, so we probably want, let's put something even higher up there. Let's put 10 up there. I'm actually not sure if that really helps us very much. Well, I guess you could put an 8 here now and put a, I guess this 30. That's not very good. No, that's not good at all. No, that's terrible. I don't know how they got 21. Let's put a 7 right in the middle there. 5, 6, 3, 4, 1, 2, 4, 9, 16. Yeah, that's fine. And then now we gotta take care of the rest of the stuff here. Put a 10 over here. 11 and a 12. No. So bad. Yeah. You definitely want to do something like this. Has got to be here. And something's got to go above this. I guess 9. I don't know. If you do 8 here. No, you don't want to fit anything else in here. You definitely want to do 9. So that's 20. And I guess on the left side, there's something else. What's this? 8, optimal for 8 is what? 11? 12. Yeah. Oh, I did this wrong, but I think I'm still right. The right side is n minus 3 plus n minus 1, yeah? And, oh, it's not, no, it's not n minus 4. It's n minus 4 plus 9. Why did I get... n minus 4 plus... No, it's just n minus 4 plus get money amount of n minus 5. I think that's what... Yeah. I think I actually did have it right, the first idea. The problem with this, though, is that when n is 5, I'll turn that the correct value here, which is 6. Well, actually, at that point, I don't think it matters. What does it? Yeah, it does. Yeah, it matters. Let's give that a shot. I'll put 20, 21. What is wrong here? What is wrong? No, man. This should give us 21. This 8 is 12. And that's n minus 3. That actually makes a lot of sense. It's my mistake. No, what? What is going on? This should be 9. This should be 12. This should be 21. 9. This is 9 plus 11 is 20. Why is this happening? 7. Oh, that's why, because it's n minus 4. I don't need to do that. Okay, I'm losing my mind. Okay. I don't know what I'm doing. Oh, okay, great. Still wrong. That's good. I don't know, man. I don't have to think anymore. I don't have to think anymore. I'm going crazy. Look at the last two at the bottom, 20 and 21. We could just do 20. I really need to go to bed. It's taking way too late here. Oh wait, I don't work tomorrow. Oh, that's awesome. Sweet. Put us 20. Okay. Alright, so now we're shooting too high somehow. Okay, that's a lot of numbers. So basically I said, okay, we'll do 20, 18, and 20. 19, 18, and 20. And then 17. And then we want to so 17, and then we want to put something else up here. We could throw 16 here. Or we could even do 15, 16, 14 here, and then put 13 over here. Yes, this is where things get interesting, right? So you can actually throw another piece here instead of just assuming everything goes on the left side of 17. Excuse me, basically giving 17 another parent node. And then here you might want to do this recursively, this part. But that's where things get interesting, I think. And if you do it this way, then the worst possible looks like this, which is 13, 17, 19, which is 49. Which is expected, right? Okay, there you go. So basically, we kind of want to fit as many nodes as we can into the right subtree, without generating another parent. I want to say, yeah, 20 is exactly where we start having a problem, because at 19, if we did 19, '19, 18, 17, and then we did the same thing, 16, now we have 14, 15, and 13. We do all of these things. Now we have 12. And now we can do 11 recursively, right? And here, this gives us 18 plus 16 plus 12. That's 34 plus 12. It's 46. However, that's not quite as good as doing 16 as the parent, and then recursively, right? Because then you do 16, 18, it gives you 34, and the recursion on 15 is right. There's a recursion on 12 and 15, which is 21 and 30. So this is, what's 19 actually? I think it's 46. I think you get the same answer in both cases. Oh yeah, look at that. 30 plus 16 is 46, and then over here this is 30 as well. This gives you 42 on the left side, but this gives you 46. So actually, after 12, things start to get interesting. I think it's still pretty good. That seems up until 20 is when you start to see problems. Oh no, this is at 19. Yeah, this is. Yeah, 19 is the breaking point. Right. Before, as I was saying, before 19, or at 19 rather, either one works, but after 19, you would want to have one more parent. What does it all mean? So basically, this heuristic that I was looking at, this doesn't really work either. Just assuming that this is the parent is not going to cut it. You can kind of guess whether or not that, you could do like kind of a loop where you could decide whether or not that should be the parent. We could also memorize this function too to make it a little bit faster, but basically you would, if you don't make it a parent, then depending on the depth, you would want to fit as many nodes into sort of the rest of that subtree, fill out that subtree. So depending on the depth, you can kind of figure out how many nodes it's going to be, and then go one level up, and then test to see if that's better or not. And then go another level up and test again. You can kind of just make a while loop. So I think I could come up with an algorithm for this. That's not too complicated. It's kind of hacked a little bit, but yeah, kind of recursion, memoize it, make it recursive, memoized, and that should be relatively efficient. But I don't want to keep messing around with this. I kind of want to go to bed. So we'll do this. I'll just say call this a part 1 when I upload the video, and come back to this problem. Make a part 2. Hopefully make it pretty quick, part 2. So yeah, thank you for watching. I appreciate it. I will talk to you all soon. Have a good rest of your night. And yeah, I'm going to get going here. I'm very tired, and this problem was pretty challenging. So yeah, take care. Take care.